Okay, it's 4. So round of applause for Pascal. He's going to be talking about parallel programming.
Okay, thank you very much. So thanks for the introduction. So I'm going to talk about the Pargo library. What is Pargo? Pargo is a library that we developed at IMEX Exascience Lab here in Belgium, and it's a library for parallel programming in Go. It's based on our experiences with lots of different other parallel programming exercises and languages in C++, Common Lisp, and Java, and a few others. And we released it under a BSD-style open source license at this URL that you can see right there. And it supports lots of different features for parallel programming. So it's based on the notion of divide and conquer task-based parallelism, which I'm going to explain in a minute. It supports lots of features like parallel ranges, parallel reduction, parallel Boolean functions, speculative parallelism, some concrete algorithms, primarily sorting, so parallel quicksort, parallel merge sort, a parallel hash table for performance, and some parallel pipelines functionality that is inspired by the Java parallel streams that was introduced in JDK 8, but with a distinct Go flavor. So we support contexts, we support cancellation, and we support Go-style error handling, of course. Now, some of you might wonder, why do we even need a parallel programming library for Go? Don't we already have concurrency mechanisms in the language that already give us everything that we need? And here it's important to stress again that concurrency and parallelism are two completely different topics. So what's the difference between concurrency and parallelism? Concurrency, you need concurrency when it's part of the problem domain. That's a really important thing to understand. So when do we have concurrency in a problem domain? One typical example is when you have an airplane reservation system. It may happen that several different people want to book the same seat at more or less the same time. Then you have a concurrent problem that comes from the problem domain that you need to solve somehow. And Go is really good at this. So you have Go channels, Goroutines, all these lovely features that allow you to really solve these issues from the problem domain. You would have these problems even if you wouldn't have multiple nodes, if you wouldn't have multiple cores, if you would have a single box with a single CPU core, you would still have to face these problems and express them somehow as a solution. And it's indeed the case that there are concurrent programming languages in the past that did that. So there's nothing about multi-core or multi-nodes here with regard to concurrency. On the other side, when we talk about parallelism, we're only talking about the solution domain. So these are problems for which we don't necessarily need any form of concurrency, but we may want to use multiple cores or multiple nodes to make them faster. That's the only reason why you would want to use parallelism. And if you don't care about performance, you can go home now. Now, sometimes it gets confusing because, of course, you also want your concurrent programs to be fast. So bringing multi-cores and multi-nodes to concurrent programs actually makes sense. But it's still important to keep these concepts separate in your head. So let's look at an example for a parallel program. So this is a very simple non-parallel program. It's a purely sequential program. It takes a slice of numbers, sums them up, and returns the sum. So nothing in here asks for parallelism or concurrency. It's a purely sequential program, perfectly fine. But maybe your slices are really big and you want to use multiple cores to make this go faster. And then one way to express this in pure Go without Pargo is by expressing it like this. So this uses Goroutines for speeding up this sum function. So the first thing is we look at a particular threshold. We ask, is the length of the slice lower than the particular threshold? And we need to experimentally determine that threshold. And then we know if it's below that threshold, it doesn't actually make sense to use multiple cores because this will be fast enough as a sequential program. If it's bigger than that threshold, then we divide the size of the slice by 2. So we split it into 2 halves. Then we use a weight group, which is a feature that comes with the Go standard library. We tell the weight group we're going to spawn one Go routine, And inside that Go routine, we're making sure that we tell the wait group that we're done after this Go routine has finished. And in that Go routine, we're building the sum as a recursive call for the left half of that slice. Then we're also building the sum for the right half of that slice, which potentially runs in parallel with the left half. Then we wait for the left half, and then we just build the sum from left and right. That's one way how to express a parallel program. What's important to realize here is that we have two recursive calls to the sum function itself. So in every recursive call, we do the same thing again. Is this now below the threshold? Then we just do the sequential version. If it's not below the threshold, we split it up in two halves again. This creates a task tree. This is what the notion of divide and conquer task parallelism means. So we split up our problem into smaller and smaller pieces until we arrive at leaves that we can do sequentially. Now this looks like a little bit of too much overhead. Why do we just create such a task tree? Why don't we just split it up by the number of cores and be done with it? Well, the beautiful thing about these kind of task trees is that they are very, very flexible to schedule. Let's assume you're on a system. So we're looking at this without the calls. Let's assume we're on a system with 16 cores. Here we have 16 leaves. So each core can take care of one of those leaves. Now assume we have 4 cores. Then each core can take care of one of the subtrees of this tree. So here we already see that no matter how many cores we have, it can flexibly adapt to how many nodes it can process. And if the more cores you have, the finer grained it becomes. But what's even more important is we simplicity made the assumption that each of the leaves more or less takes the same amount of time. But it's very often not the case. Very often the leaves have different run times. This is when you talk about load imbalance in parallel programming, which is a big issue in parallel programming. With this kind of task tree, it's very easy to solve. Some of the cores will just take care of the heavyweight leaves, which just takes longer. And at the same time, some of the other cores will just take care of more tasks until the whole program is done. And this is a very beautiful and elegant solution for dealing with load imbalance. And as I said, this happens much more often than you might think. So, task-based parallelism allows for flexible distribution of work over CPU cores. If the typical case, what lots of newbies typically do when they do parallel programming by just dividing the number of the work over the CPU cores statically, typically leads to bad performance and is not optimal. But what I haven't explained yet is how do we actually schedule the task tree? So I just said we can schedule it over multiple cores flexibly, but we haven't yet explained how. So the elegant solution for that is work stealing. So work stealing is a known concept, at least since the 80s, formalized in the 90s. Here's 2 really excellent papers that explain what work stealing does. And the idea here is that each core basically looks for work and steals whatever it can do. This has been successfully implemented in many programming languages and libraries. It has been implemented in Silk for C. This is the most famous one. It has been implemented as threading building blocks for C++. It has been implemented as Java fork join library, which comes with the Java default library. And it has been implemented in Go. The scheduler for Go routines in the standard implementation of Go is actually a work stealing scheduler. And this was the main reason why we became so excited about Go, to use it for our parallel programming tasks. So what does it look like? Assume you have 4 cores, and one of the cores starts working on creating such a task tree. So what it does is there's one task which then spawns another task, and at the same time the other cores are just asking each other, do you have any work for me to do? One of the cores will, by chance, pick one of the tasks from one of the other cores and just continue working on that. In the next step, the original core creates another task, and some other core randomly gets that task by just stealing it from the first core, and so on. Once every core is busy, they're just continuing to work on their own tasks, creating new tasks, finishing other tasks, until one core may be empty, and then it just starts looking again. Does anybody have work to do? And just steals it randomly and continues. So this is how work stealing very roughly works. There's lots of details, technical details, to make sure it's really efficient. But what's really beautiful about work stealing is you don't need to plan anything. These kind of work distributions that deal with load imbalance basically just emerge out of cores randomly looking for work. And it's known, based on these papers that I've shown, that this is actually optimal. You can't do better than that. And that's why I believe Go probably uses this, and why we are very happy that this is available in Go. So now back to our original example. What you see in this code is there's a lot of a management code that just makes sure that we can create work, distribute it, spawn it, make sure that we wait for it, and so on. So lots of code that we're not really interested in. And this is where Pargo comes in. So Pargo uses this notion of divide and conquer task parallelism, and then gives you a couple of higher level functions to make it easier to use this. So in Pargo, the same program looks like this, and under the hood essentially has the same implementation. So here, this particular example is an example for a range reduction. So we arrange over a slice and we reduce it. So reduction is a term that is known in parallel programming. We reduce many values to a single value. This doesn't have anything to do with Hadoop MapReduce or so. This is a parallel programming term. And then we need the base case, which is a sequential base case. This gets called by Pargo, and Pargo tells it which part of the slice should I be looking at. And then you need a reduction function, which just tells the Pargo library, okay, if I have two results, how do I combine them? Well, I just add them. So this does exactly what I described before under the hood, just makes it much easier and much more elegant to describe it at a higher level. So this is where all these functionalities that are already sketched come into play. So we have a simple parallel do, which just spawns a couple of Goroutines functions. We have ranges, which don't produce a result. We have reductions over ints, floats, strings, and generic interface. We have range reductions over int, float, string, and generic interface. We have the Boolean functions. We have speculative versions, which are especially interesting with the Boolean functions, because you can make sure that a tree stops executing as soon as you already know the result. We have sequential variants, which is not supposed to be used in production code, but it can be used when you want to debug your programs, especially when you want to do print line debugging. We have the quicksort and merge sort, which are actually quite complex algorithms, so we hide this away from you. And parallel hash tables and pipelines. Now here again, people may wonder, why do we need parallel pipelines? Go is already really good at pipelines, and that's true. So here's an example of a pipeline in Go, which I took from a tutorial. It's a two-stage pipeline. The first stage just gets a slice of numbers and just creates a channel over which these numbers are sent one after the other. The next stage takes this channel of numbers, squares each element, and then sends the squared numbers to the next channel. And then here is a main program that just reads the squared numbers and prints them out. For a concurrent program, this is really beautiful, really elegant to read, very easy to work with. From a parallel perspective, this is not so great, because we just created 3 Goroutines. Now, if you have 16 cores, there is now 13 cores that don't do anything. But you want to keep them busy because you're interested in taking advantage of them for performance. So you would like to distribute the work a bit differently when you're thinking about a parallel program. So I'm not saying this is bad. For concurrent programming, this is really elegant because you're probably also dealing with many of these pipelines at the same time. So you're already creating a lot of work. But for parallel perspective, it is quite likely that this is the only pipeline, and then you want to distribute the work differently. So here is a pipeline in Pargo. What we do here is we Pargo, a pipeline is a data structure. The null value can already be used. We give it a source. In this case, it's a silly source. It's a slice of two numbers. Of course, you wouldn't use a parallel pipeline for a slice of two numbers. This is just for an example. Then you can add stages. The first stage is a parallel stage. It receives a batch of numbers. It's hidden behind an interface because that's the only way in Go to declare something generic. It unpacks that data into a slice of numbers, then modifies this in place to build a square for each number. And then the next stage is an ordered stage. Ordered stage means it's sequential. So this stage doesn't run in parallel. And it is executed in exactly the same order as the source of the pipeline. And here we can just print out the result. What's nice about this here is now that in the back, we again use this principle of divide and conquer task parallelism to split up the inputs into batches and create more batches than are cores available so that a work scheduler can actually optimally schedule them. And this is how you can take advantage of all your cores. I forgot in the end, you just run this. So what you have in the parallel pipelines in Pargo, you have predefined pipeline sources for arrays, slices, strings, channels, and buff.io scanner, so for scanning text files. You have support for user-defined sources through the source interface. You have support for several kinds of nodes or stages, so sequential, ordered with a guaranteed order, parallel. You also have strictly ordered and limited parallel, which gives you a way to control how much memory is used. You have skip and limit nodes, where you can skip elements or you can limit how many elements you want to see over the lifetime. You have support for several kinds of filters, so generic, receive, and finalize, Boolean filters, where you can ask only run as long as every package fulfills a certain condition. You have counting filters, just counting how many elements you see. And you have slice filters for producing result slices. We also support contexts with cancellation, error handling, Go-style error handling, and fine-tuning of batch sizes so you can really tweak the performance. All of these features are not just something that we just made up and came up with. We actually use this ourselves. So we have one tool called ELPREP, which is a DNA sequencing tool that we developed already for a couple of years. It's a high-performance tool for doing certain steps in the DNA sequencing pipeline. It is a multi-threaded application that runs typically something like 10 times faster than the standard tools. And it runs 10 times faster because we're using the Pargo pipelines and some of the other Pargo functionality that I just described. And it's implemented in Go since version 3.0, and it's available as an open source project here at this link. So we're eating our own dog food, and we're making this available so you can also use it in your projects. So Pargo is available at this URL. Documentation is also available, so the standard API documentation and the wiki, which describes the concepts in a bit more detail, which can't easily be described as API documentations. There's also a link for ELPREP, and that's the end of my talk. Thank you very much. Do we have? Sure.
So my question is, the code that you showed looked like something that would benefit from generics. What do you think about contracts?
I was hoping I wouldn't get that question. I'm not a big fan of generics. And I think Go would be better off without generics. That's my personal conviction. From a user perspective, generics look elegant, but from a library provider perspective, it becomes incredibly hard to write them correct. And I'm not really happy about the current ideas around the contracts, because that was just a hack in C++, that kind of a coincidental hack, like many things in C++. And I don't think we should imitate that in the Go language. That's my personal opinion. Okay. I'm the microphone runner myself.
Do you have any particular performance metrics between something using Pargo?
Performance metrics between?
Yeah. Do you have any numbers for?
Oh, do we have numbers? Well, yes. So for the ELPREP sequencing tool, we actually had a paper for the previous version, which was not in Go, but we just got a notification that it was now accepted for the new version, which is in Go, and there we have performance numbers. We also did a study where we compared performance between Go, C++, and Java for exactly that tool, which I presented last year at FOSDEM, where Go actually came out as the winner. And yeah, so you can find these numbers. Other questions? Okay, thank you very much.